it's time to introduce our first speaker, which is Henrik Alexander Nissen Søndergaard, very impressive name, from University of Southern Denmark, and he will talk us about digital twin-based fault detection and prioritization in district heating systems, and it's about a case study in Denmark.
Thank you very much. Oh yeah, true. I have to have two things. So yeah, I'm going to present work on behalf of two students at the University of Southern Denmark. And the work is on digital twin-based fault detection and prioritization in district heating system with a fault with a case study as well. So let's get to it. Oh, there we go. Especially in Northern Europe and other colder places, heating constitutes a great part of the energy consumption. It is therefore very important for the energy, like reducing CO2 and generally just reducing the amount of energy we consume, to focus on district heating in those parts of the world, so we can save money and save the world, so to say. So that's why this work here is focused on improving the energy efficiency and in general the operation of district heating systems. So one problem that is very often in district heating systems is that they just are put in operation and then they just wait till something breaks and then they finally fix it instead of proactively fixing stuff. So that's the problem of continuous commissioning. Very often it's done on a reactive, where it's fixed when broken, as I said, and also sometimes on a planned schedule, which is also very inefficient very often because you sometimes investigate stuff too often and waste too much money investigating things. So instead, we want to move towards smarter solutions that are, for example, proactive and also predictive. But in this paper here, we are looking more into the proactive aspects. So we want to move from reactive and planned maintenance, which is efficient, to monitoring the system by doing proactive maintenance. And this is not something that is widely done in Denmark, at least. So this is a step forward in maintaining and improving the system. Some of the faults that can occur can impact, of course, the occupant comfort of the users using the buildings. Very often these faults are detected very quickly because people are going to call in and say, I don't have heat. So these are not always the type of problems that we want to detect because people just report them by themselves. But we want to look at identify things that even though the system operates, it's operating inefficiently. You can, for example, lower the forward temperature so there's less heat loss in the system and also decrease the return temperature. Yeah. So overall, we want to improve the maintenance of the system when they're in use. And we can do this with the use of fault detection methods. So they can enable real-time monitoring of the systems and then reduce the energy waste via early detection instead of waiting till it breaks. So you can very often see in data that a fault is building up and then catch it early. And then we can also better allocate the maintenance workers' time instead of them just doing whatever they want. Give them something more concrete to investigate instead. So there's a general gap in the fault detection in district heating that very often these methods that are introduced, they detect too many faults. So the maintenance crews might be looking at a long list of things. Oh, these methods detected 1,000 faults. Where do you start? That's very difficult to say, and they can't really even use it. And sometimes they just throw it out and say, yeah, we won't even use this. And also model-based fault detection methods are not widespread in district heating, and that is what we'll focus on in this paper by creating a digital twin of a district heating system. And also the data currently created in the district heating systems are not used to their full potential. Very often the data from consumers is just used for billing and some simple calculations and so on. So the contributions of this paper is utilizing a model-based approach in district heating for fault detection, and then implementation of a fault prioritization methodology. We can kind of rank the different faults that are detected, so they know where to start the maintenance crews, and then an overall framework encapsulating those two aspects, and then using a case study with actual data from an actual district heating system to showcase the methodology. And in general, we contribute to the digitalization of the heating sector. So the proposed framework is it's kind of set up as an automatic fault detection and filtering of the faults that are detected. So first, we have created a digital twin of the system using the sort of like pipe data and so on, and then we simulate the system with some boundary conditions from the actual sensors, but some are then calculated that are not boundary conditions, and then you can compare the actual measurements to what the output of the digital twin is, like the model of the system. And then this is then presented to the output of this after some filtering is then presented to the maintenance workers as a list. Very simple. And in this paper, we only apply the methodology to the consumers' smart meters. So we actually only have data from the end consumers and also a pumping substation, so the border between transmission and distribution grid. That's kind of the limits of this methodology here. So just again, we use a simulation software called LeanHeat. It's not something we developed, but it's something by Danfoss, which is a Danish company, where you can draw your grid and insert boundary conditions, and you're able to simulate the grid and export the data. It simulates like the hydronic and thermal conditions of the grid and optimizes the supply temperatures and pressures. And yeah, the data inputs are the consumer data, the endpoints of the grid, and then the pump substation data and all the pipe data, like static pipe data. So when you wanna, as you see in this step here, you kind of simulate and then you compare the sensor data to what was actually the sensor data to what was the simulation output was. And then you kind of want to see that, okay, maybe that's a small difference, but that's not the fault. That's just a small modeling error. So we set up some small bounds using root mean squared error. So it has to be above a certain bound, plus minus, to actually be detected as a fault, because to reduce the number of faults that are presented. But that's the first step of filtering. So this root mean squared error is based on a training data, where they calculate, that's kind of how bad is it at predicting, and we assume that the data in the training data is fault-free, but we're not sure of that. Obviously, that takes a lot of effort to figure out if that's actually true, but yeah. So then we actually use something called Chernoff bound, which has been used in telecommunications and also in building systems to view using just data. It's kind of set what is the probability of this being a fault based on how far above a threshold and for how long it is above the threshold. So it's a combination of those two things. So as seen on the picture here, you can see the target is the green line, and then which is what the simulation produced that we assume is the best situation for the system to operate at. And then we have the bounds, which are in black. So when it goes above or below the bounds, it starts calculating the Chernoff bound. And then depending on for how long below or above and for how long time it is below or above, it gives a certain probability of it being a fault. And then you can then afterwards you rank these probabilities. And the thing is also that when we go from this, before each singular violation of the threshold was a fault, so to say, and here it's actually moved more towards events. So it's the combination over time, the whole thing is considered a fault and not just each single observation. The assumption here is also that the further away you are from the model, the more likely there is a fault. But is that always the case? That's the question, but that's what is assumed in this work here. And then here you can see the output of the model, the time and the end time. It's like an event, the fault probability, and also it's categorized into different categories, just high, medium, and low. And then the case study is a distribution grid in Odense in Denmark. It's downstream from a pumping station, and there's 648 consumers. And you can see the boundary conditions are the consumer return temperature, consumer heat consumption, and then the pumping station supply temperature and pumping station return temperature. So those we cannot actually perform the fault detection on because they will be equal between the simulation and what the actual measurements are. But then all the others that are simulated and determined in the simulation, we can compare to the real sensor measurements. One thing that is very important, as you saw in the root mean squared error, is you can also kind of increase the bound. So that's the first way of filtering. So first, if you set it to 1 standard deviation, 1,500 faults are detected. But then we can kind of increase it just like an initial filtering of the faults. So it's all kind of striking a balance between what you want to present to the maintenance crews and they still want to detect something. And here you see just an example from a normal operation. The 2 bottom plots are boundary conditions, and this is just for one consumer. And the 2 upper plots are the flows of the water and the supply temperature. You see it's like a pretty good match. And here no faults are detected. And here you can see some example of some deviations where there's actually bad cooling at a consumer. The problem is this bad cooling because of some problems in installation or because of behavior from the consumers. But the district heating company did validate that this was a cooling problem that they have investigated afterwards. So the method was able to detect that. Where you can see that the difference between forward and return temperature are very close together. And then the flow from the simulation increases a lot. And that's not very bad. That's not very good for the system because you have a lot of losses and the grid cannot handle too large flows as well in the pipes. And then we have one issue actually with the simulation where it's not actually able to handle all operation in the systems. For example, you see here, the flow here is almost 0 and the model it actually changes the boundary conditions that we gave it. So there's some problems with some operation that is not able to handle the simulation. One thing that we also kind of investigated when is one easy way to kind of locate the faults, because right now we only look at the end consumers and we don't have any idea of what is going on in between, and that's actually something the next presentation is going to tackle. But one simple thing you can kind of look at is if there are multiple faults in the same geographic area that has happened, maybe perhaps it's upstream the problem is, or it's perhaps the kind of building that is in question. There were 3 faults at the same time that happened, and all of them were terrace houses. And in general, there's a lot of faults at terrace houses, so that's something for further investigation. And then, in conclusion, we were able to create a framework for detection of faults utilizing a model-based approach. We were able to integrate Chernoff bound as a way of prioritizing the different faults. So we can only help the maintenance crews, not just give them a long list, but help them. You can start from the top and then try to investigate. Of course, it's still just a probability of fault. We're not sure there's actually something, but at least it's a higher chance that the ones that presented first actually are a fault. And the faults that were we detected were verified by the district heating company. And yeah, for future work, we want to do more real-world implementation. Right now, it's just a very small part of a grid, and we didn't do fault detection on the substation measurements. So we wanted to include more larger part of the grid. You were able to do that as well. And we want to be able to identify what type of faults. Right now, we just detect them, and then afterwards manually discuss with the district heating company what was going on. And then one thing, that's it.
Thank you, Henrik. And thanks for perfectly keeping time. Are there questions from the audience? Yeah.
So it's very interesting presentation. Thank you very much. I was just wondering, could you elaborate on the impact of the model accuracy and the sensor accuracy as well on the FDD strategy? Because at the end of the day, like the model might not be perfect. So at some point, like, does it come from the model? Does it come from the real system? So could you elaborate a bit more on that? Maybe like the selection of the model or something like this?
Yeah, so it's not something we've looked that much into. We just kind of assumed, yeah, we created a model. We kind of assume that it's a good model, but we'd still increase like the bounds just to say, it's probably not perfect. We want to decrease the number of faults that are detected, but it's something that has to be further investigated, like properly verifying the model, which has not been done thoroughly, at least in this case. Have to implement it on more parts of the system. This is the first time they probably did this on a part of the system using the new methods and using this methodology. So I hope that kind of answers so that we can discuss.
Okay, there was another question here.
Yes, thank you. Thank you for a nice presentation, Henrik. I was wondering, what are the most common faults that we experience in the district heating grid, and what are the common causes for those faults?
Yeah, so at least at consumers, what they very often see and what they are also actively investigating at the moment is just bad cooling. When there's low difference between the forward and return temperatures, which decreases the overall efficiency of the grid, and that has a large impact on the efficiency of the grid. And that can be both either due to how they use the heat, like their behavior, or some fault in the actual installation of this, like heating installation. And on top of that, something that cannot be detected here, but is like something that is also a great focus is leaks in the pipes between the end consumers and the production all the way at the beginning. Lots of wasted water, and that's something that's been targeted in a while with the drones going over and measuring the temperatures in the ground. But yeah,